we covered up for, we actually did work for 2 weeks. So we covered up for 1 week. We covered up for 1 week last week. Okay. Yeah, so we already covered up for last week. So today, knowledge rep is the equivalent of 2 topics. It's an equivalent of 2 topics, and we'll find a way of fast tracking. Thank God some of these things on knowledge rep you have done under critical thinking and a bit of maths, a bit of issues in mathematics. So, but we'll confirm that in a while. Okay, so knowledge rep today. For those who are not there, we have other topics: reasoning systems, topic 4, problem solving in AI, topic 5, machine learning, topic 6, NLP, game playing, and planning in AI. So I didn't put practicals directly here, but of course you can see from the details we have to the right in terms of comments, under comments. We'll do a bit of practicals after knowledge rep. We'll also do part of that under machine learning when you're looking at the algorithms. So we'll find a way of handling that. Okay, so we can now move to knowledge rep unless somebody has a question on 1 and 2. Maybe you can allow me to ask a question on 1 and 2. Okay, Andre, it's okay. It's okay. If you can hear now, we appreciate it for that. Now, for those who attended last week, just one question on introduction to AI. I think Osborne was there. Osborne, what was our definition of artificial intelligence? Or in your own words, can you try to explain what artificial intelligence is using your own words? Osborne, you can try. Those who cannot speak can also type. You can just type something there. Say something about artificial intelligence. Anything about AI. Osborne. Anyone who can attempt. We want to do a bit of recap quickly as we move. Kelvin, you want to try? Okay, carry on. Okay. Yeah, that's a good trial. Thank you, Kelvin, for that. It is a branch of computer science that attempts to create machines that can think rationally, act rationally, think like a human, or act like a human. That was the elaborate definition that we gave. So we assumed that human beings are intelligent, and so when we attempt to come up with a system that is able to mimic a human being, then that system automatically becomes an intelligent system. Okay. So that is artificial intelligence. So intelligence simply is the manner in which we solve problems. So any machine that is able to solve problems in a way that humans do is an intelligent machine. All right. Osborne, you want to try now?
I had some technical.
Okay.
I was
Then it's okay. If you are not talking, you can just unmute. Then you can mute. Huh?
Yeah.
Okay. Very well. Levy is an attempt of reproduction of human reasoning and intelligent properties or capabilities using computational methods. That's correct. So we attempt to reproduce human reasoning and intelligent behavior, And of course, we are using computational methods. So that is artificial intelligence. Maybe a quick set of applications of AI. Where do we apply artificial intelligence? We can look at the industries, we can look at schools, we can look at mobile phones, etc. So just quick applications, one or two. Quick applications. Yes, Anjoy?
We can in robotics.
Okay, very well. Robotics
and automated systems.
Okay, good. Robotics, automated systems. Levi is confirming robotics. Thank you, Anne. Thank you, Levi. Robotics. Somebody else? Another application? Levi is typing another one. Okay. So in mobile phones, we have intelligent systems that we normally use. Huh? Okay. When we are doing search for information, we use AI systems. Bilimo, game playing, that's okay. Game playing, okay. In mobile phones, we have agents, especially that do NLP. Levi has confirmed NLP, which is still okay. So that is natural language processing, etc. So AI, we are attempting to reproduce human behavior, human reasoning, intelligent behavior of a human into systems. Okay, so coming up with systems that are able to do that. Very well, we looked at agents also in topic 2, agents. And agents are basically systems that are able to perform tasks on behalf of users. They can do certain things on behalf of different users. It can be about search for information. It can be about implementing human behavior like motion or locomotion, performing certain tasks, okay? Either normal tasks or tasks that involve reasoning, etc. So agents are able to do that. Multi-agents are simply 2 or more agents put together that coordinate. And of course, they perform certain tasks on behalf of users. Maybe on agents, somebody can quickly give us properties of agents, properties or characteristics from what we discussed last time. Properties, characteristics of agents. Yes, Bilimo?
We have mobility, the ability of moving around the network platforms.
Thank you, Bilimo. Mobility, that is motion, moving around. Anjoy?
Yeah. There is proactiveness, reactiveness, with responding to changes in the environment.
Yeah, so reactiveness or reactivity, that is responding to changes in the environment. You also mentioned proactiveness. That is proactivity, performing tasks on its own, that is own initiative, proactiveness, etc. Those who are not able to talk can type on the public chat so that all of us participate. Yeah, so those are some of the properties that we looked at. We have independence, that is autonomy. We have mobility, we've already talked about that, etc. So different properties of agents that we can implement. Yeah, then we said an agent operates within an environment, and environments can be either physical or virtual. You can have a network as an environment. You can have a classroom or an industrial setup or the road, okay, the normal road that we have, or railway line or road as an agent, as an environment. Of course, we have self-driving cars, which are also agents that can be operated on the roads. So maybe finally on agents, how does an agent get information from the environment? That is perception. How does an agent perceive the environment? What does it use to do that? And what is an example of that? Yes, Osman?
We have sensors.
Yeah, an agent uses sensors. Any example of a sensor?
Sensor can be maybe microphone.
Sorry?
Maybe microphone to
Yeah,
get the, if it's a
audio.
sound. Yeah, audio.
Yeah, good. Microphone, for example, for audio. So that is, they use sensors. Sensors. Any other examples of sensors? Anyone else? Examples of sensors randomly? Sensors. That is how an agent gets information from the environment. It actually senses. Okay. Let me say the screen. Maybe a smart screen. Smart screen, like a touch screen. If you can implement that in a robot. So you can get information that way. We talked about camera. Camera. An agent can get information using a camera. Okay, that will facilitate vision. Oh, Gerald, thermometer. Okay, thermometer. So we have agents that are used for, rather that athletes normally use. As we mentioned last time, maybe there could be a thermometer or something of the sort that would retrieve or get temperature and act accordingly. All right. Very well. The second part is how they act on the environment. How do they act? What do agents use to act on the environment? What do they use to act? Somebody? Somebody? What do they use to act? Yes, Anne?
Actuators and effectors.
Okay, actuators stroke effectors is the same thing. For example, any examples of actuators?
For example, wheels.
Okay, wheels for movement.
Movement, yes.
Thank you. Osborne is saying hand or legs. So the hand as a whole or fingers, you can use that. You can use legs. Sometimes you call them limbs for movement, etc. So an agent retrieves information from the environment, that is, perceives the environment using sensors, and agents act on the environment using actuators. Yeah, using actuators, okay, on the environment. So that is good. You will read more on the same. So there is an array of examples. For a network case, we talked about search engines. Search engines, they get information and then they give us. In a physical environment, we have a robot, okay, which can move around an industry and perform certain tasks. We have self-driving cars, which you can have on the roads, and they're able to operate on their own, etc. So those are a number of examples of agents that we can use. Okay. Yeah, so you can allow me now to move to knowledge representation, unless somebody has a question. I can now move to knowledge representation, and you'll allow me to share. If you have a question, you can just type or activate your mic and speak. So, picking up from the agents, agents in AI normally use knowledge for reasoning. They depend on certain information. This information can be obtained through learning when they learn, or they can get it from information that is stored. And it is stored in a manner that they can use, rather, in a manner that they can manipulate and use it for intelligent action. Okay? So they need some knowledge, they need some information. Now, we defined knowledge last time in our last class, that knowledge is simply domain-specific information. Domain-specific information, that is knowledge. An individual's understanding of a given subject or information on a particular domain, which can be used to solve problems or can be used to handle a number of issues here and there. So we call it domain-specific knowledge, domain-specific information. Domain-specific because it covers a particular subject area, For example, ICT, maths is so wide, so you can have information in statistics, for example. Statistics is also wide. You can have information on maybe measures of central tendency or measures of dispersion, okay? And you can continue moving closer and closer or further and further to have more specific information that you'll be able to handle. So that is knowledge. There are different types of knowledge. One is declarative knowledge. Declarative. So declarative describes what is known about a problem. Information about a problem, which is either true or false. It is something that has been researched. It is something that is known. It is a description of an object or simply a concept. So we call it declarative knowledge. Information, concepts, facts, description of an object, something that is known, like the concept of AI that we are discussing. That is declarative. Okay. Number two is procedural. Procedural knowledge is equivalent to a rule, a strategy, an agenda, or a procedure. It is simply a set of information that explains or describes how to solve a problem. How to solve a problem. So, what are the set of steps? What is the information put together that is able to provide a solution to whichever problem that is handled? And in mathematics, you guys have formulas. So the description of a formula is equivalent to procedural knowledge. And we use that in IT or in computing, and we normally call it algorithms. When you'll be doing programming, you'll come across that. So that is procedural. Number three is heuristic knowledge. Heuristic knowledge is also called the rule of thumb. Okay, it is a set of knowledge that guides reasoning process. Okay, the rule of thumb that guides reasoning process. So it means it is knowledge or information that has already been researched, and it has been concluded that that is how we can, that is the process that we can use, or the information that we can use in a particular reasoning scenario. Okay, the process in some reasoning scenario. Yeah. Okay. Yeah, sorry, Jacob is asking what we are talking about. The topic is knowledge representation. Thanks, Andre, for helping Jacob. The topic is topic 3, that is knowledge representation. So heuristics is the rule of thumb, how to do things, how to solve a problem. Okay, something that has been confirmed, that is how we normally do it. So it is empirical and represents knowledge compiled by an expert through experience. Empirical simply is when we go through certain practicals. You can do some practicals and then you come up with a documentation on a practical way of providing solution to a problem, one or more. The last one is called meta-knowledge. Meta-knowledge is simply knowledge about knowledge, knowledge that describes other types of knowledge. The description is normally done in a way, that we enhance the effectiveness or efficiency of problem solving, or we do it in a way that explains knowledge further. You have some information and you want to proceed, okay? You want to proceed with other details. All right, so effectiveness or efficiency of knowledge. Levi is asking how AL affects us Us here would mean mathematicians. You guys are doing mathematics and computer science. One, you will be doing programming. You will program. Oh, thank you, Diana. You'll program. You'll come up with algorithms and programs for certain. Okay, you are supposed to be providing solutions to problems, solutions to certain problems that exist. You're supposed to do that. So you'll be doing programming. Number two, in mathematics, you do modeling. And one of the things that you'll be able to model or you'll be expected to model are artificial intelligence systems. Artificial intelligence systems. Okay. So AI is very, it is a unit that is, it is very relevant for those doing mathematics and computer science. Are you still getting me? Please confirm if you can still hear me. Bilimo, can you hear me?
Yes, you are still clear.
Osborne?
You are still clear, sir, but can you please re-explain that the types of knowledge?
All right. Yeah, Levi, you can reconnect because your colleague can hear me. So Levi, you can just reconnect. Then I think your network will be okay. Oh, sawa. Oh, sorry. There's just something I've added on knowledge only. The rest are the same. In terms of the notes, Diana, I've only added the types of knowledge, but hizo zingine zote ziko sawa. I will maybe update so that I include this. Yeah, so let me redo the types of knowledge. Meta-knowledge is knowledge about knowledge. Then the last one is structural knowledge. Structural knowledge is simply a type of knowledge that describes an expert's overall mental model of a problem. That is, how an expert sees or analyzes a particular problem and how, in the expert's view, that problem can be solved. That is what we call structural knowledge. Let me just rush through that again. So knowledge is domain-specific information. The types, declarative. Declarative is knowledge that describes a particular problem or solution. It is true or false the way it is. Declarative, and we will come up with facts or propositions, which are examples of declarative knowledge. So it is simply a description of an object, a description of a fact, a description of a problem, a description of a solution. Declaration, declarative knowledge. Procedural, method for doing something. Are they steps? You can have, for example, step 1 up to 5, how to do something. That is procedural knowledge. So it is simply a procedure. Heuristics, the rule of thumb, a particular way that has been proved, a way that has been proved of handling an issue or solving a problem. So we call it the rule of thumb. That means this is how we normally do it. So when you do it this way, you will provide or you will come up with a solution to the problem. So that is called the rule of thumb, heuristics. Heuristics. Okay, Caroline Karibu, you can unmute. Sorry, you can mute. Then we have meta-knowledge. Meta-knowledge is knowledge about knowledge. That is knowledge that describes other types of knowledge. Okay, it describes so that the knowledge is clearer or problem solving is enhanced. So it is simply knowledge that describes other types of knowledge. Structural knowledge is the mental model of an expert. How does an expert view a problem and how it can be solved? So when that is documented, then we call it structural knowledge. So it is basically the problem and the solution in the eyes of an expert. Like you guys are going to be, somebody may lean on the side of mathematics, somebody may lean on computer science. So as an expert in that area, you can come up with your way of doing that, or rather coming up with a solution to the same. So knowledge representation is simply a way of putting together this knowledge, either one or a number. You can choose two, it can be a hybrid or just a particular type of knowledge, putting it in a way that can be used for decision making. Okay, representing, arranging, organizing the knowledge, or putting together knowledge in a way that intelligent agents can use for problem solving or for reasoning. Okay, so it is simply how we express. It is a method or a way of expressing knowledge in a way that systems can consume or use the knowledge for reasoning or for providing solutions or for making intelligent moves, okay, within the systems. So that is what we call knowledge representation. We have different methods of representing knowledge. Method one is propositional logic. You can see it on the screen there. Method two is first order logic. We also call it predicate calculus. Propositional logic is also called propositional calculus. Number three is rules. We also call it production rules. Then we have frames and semantic networks. So these are the main methods that are normally used. So I will quickly rush through the last three and then we concentrate on the first. The first one a bit long. Okay. Any questions so far? I hope you are still getting me. Still getting me?
Yes.
Okay. Sawa. So the different methods that we use, methods for representing knowledge, are those 6 that we have there. Allow me to start with the third last. The third last, that is rules. And I will just scroll down. I want to start with the simpler ones. Then we come and concentrate on the rest. Rules are also called production rules. So we call that production rules. Now, production rules are simply a combination of it is a statement that has the if part and the then part. The if part represents a condition that is set. The then part represents a conclusion that is being made. So that if a particular condition holds, then a conclusion is made. Okay, so that is basically part of inferencing. Something to do with inferencing. So production rules. We have a statement. That statement has if part, which is a condition. It also has then part, which is an action that is being performed. It can be one statement or there can be more, several statements, and all those statements assist in coming up with a solution. These are examples. Example 1 is, if high temperature, then prescribe aspirin. Now, there are a number of ways of representing these rules. There are a number of ways of representing these rules. One is you can just use normal English statement, like we have up there. If high temperature, then prescribe aspirin. Gerald, I think your network has a problem. If you can just reconnect again, I can confirm with somebody else. Sorry, Gerald is saying he's seeing the first slide only on his screen throughout. Can you confirm that we are on production rules currently on the screen? Somebody confirm for me that. Calvin?
Yes, we are in production rules.
Production rules, eh?
Yes.
Thank you. So Gerald, you can just connect again. Looks like your network has a bit of an issue. Thank you. So a production rule is simply a statement. The statement has if and the then part. So it is a way of reasoning. It is a way of confirming something. So, and I was saying we have two methods of doing it. One is just use English. You can just use normal English. For example, this is a bit summarized, but it should be something like, if the temperatures are high on somebody, then a doctor can prescribe aspirin. Okay, so that means there's fever or high temperature. So aspirin. So if high temperature, then prescribe aspirin. That means high temperature implies prescription of aspirin. So high temperature is the condition. It means for us to prescribe aspirin, then the temperature must be high. Temperature must be high for us to prescribe aspirin. So that is what we call a production rule, just one statement. Now, so we can use English, normal English. Number two, we can use alphabetical letters to represent the statements. For example, you can say, let high temperature be A. Let prescription of aspirin be B. So we say high temperature is equivalent to A. Prescribe aspirin is equivalent to B. So you say if A, then B. So this is another way of writing it. Now, point to note, we normally use letters if we know the equivalent sentences, unless we are making an assumption. So example one there, number one there is the first example of a production rule. Okay. Number two, you can have a production rule with one complex statement or several that are mixed. For example, number two, if international conflict begins and it is in Middle East, then oil prices go up. Those are three statements. International conflict begins. The international conflict mostly is happening in Middle East. Then statement three is prices of oil go up. So we can have it as a statement that international conflict and the conflict being in Middle East implies prices of oil go up. So that is just normal English. If international conflict begins and it is in the Middle East, then oil prices go up. Now, we can say, let international conflict begins be A, Middle East be B, then oil prices go up be C. Then in that case, we say, if A and B, then C. If A and B, then C, like that. So these are two examples that we have. We have other examples down there. Now, I want somebody to try to create okay. Alton anasikia echo. I hope the rest hawana echo or something. If it is my connection, I can do something. Levi, unasikia echo?
Yes. Yeah.
Kuna echo?
No, I'm not hearing that echo.
Okay. Maybe Alton, if you are two of you in the room and both of you are connected, O'Brien pia anasikia echo. Okay, sawa. Okay.
Excuse me, sir.
Yes, Levi.
Yeah, in my screen,
Yes.
yeah, I see types of knowledge. That's what I'm seeing at my screen only.
Types of?
Types of knowledge.
Okay. Reconnect again. Eh?
Yeah.
Yeah, just try to reconnect.
Yes.
Mm. Yeah, because I think my network is okay. Just try to reconnect. If the problem persists, I can share afresh. Eh?
Yes.
Okay. Yeah, so what you should have on the screen is production rules, number 1 and number 2. Number 1 and number 2. Now, I want somebody to come up with a production rule using the following statements. Number one is student pays fee. Student pays fee. Number 2, thank you, Gerald. So student pays fee is one statement. Statement 2 is student does exam. Student allowed to do exam. Student allowed to do exam. So student pays fee, statement 1. Statement 2, student allowed to do exam. So I want someone to combine those two statements so that it becomes a production rule. Who is doing that? Bilimo?
Okay, if student pays fee, then he is allowed to do the exam.
Very well. That's okay. That's okay. So student pays fee, then they will be allowed, or you will be allowed to do an exam. Now, can somebody try to do that, to come up with a production rule with 3 sentences? Maybe student pays fee and does something else, and then now does exam with 3 sentences. Levi?
Oh, if student pays school fee, yeah,
And
he is allowed to sit for the exam.
those are 2 statements. We want 3 statements now.
Oh, you see statement.
Three statements. Calvin, you
The next one.
sorry?
You can give the another chance to try. Let me think first.
Okay, no problem.
Yeah.
Who is trying? Is it Calvin? Is it Osborne?
Yeah.
Osborne, okay, carry on, Osborne.
If student pays fee, then it's allowed to.
If student pays fee and
If student pays fee,
This, the rest you can you can only mute, you can unmute, then you can mute. You unmute only when you are talking. Yeah. Calvin. Sorry, Osborne, carry on.
if student pays fee and registers, they are allowed to do exam.
Pays fee and?
Registers it.
Oh, and registers. Okay, sawa. That's okay. If a student pays fees and registers, maybe for units, then is allowed to do exams. Or Bilimo has typed, if a student pays fees and attends all lessons, then allowed to do exams, correct? Levi, student pays fees and attends online classes, allowed to do exams, that's okay. Millicent, student pays fees and registers units, allowed to do exams, that's okay. So these are examples of production rules. That means they have facts. A fact. A fact is that something like student pays fee. That is a fact. Student attends lessons. That is another fact. Okay. Student allowed to do exams. That's another fact. So when we combine them, then we come up with what we call a rule, a production rule. Okay. A rule is where we have some data or information that leads to another. A and B implies C. A implies B. So that's why we are calling it a production rule. So these are 2 ways of representing a production rule. There are other ways of representing it, especially when we are typing in the system or when we are introducing or including them in a system. Okay. So one method is using normal English. Another method is representing statements using letters like A, B, C, D, and then we arrange them using if, then, else, and stuff like that. All right. Yeah, so that is production rules. There's an example here where we try to come up with, there's this sentence, sorry, this paragraph. One lives near Muthaiga Road. One has a plum salary. One can say he lives near Muthaiga Road, etc. So this is a paragraph, and from this paragraph, there is a set of production rules that have been generated, as you can see here. If A and B, then C. If D, then A. If B and E, then F. If G, then H, like that. So this is a set of production rules that have been developed from this paragraph. So a production rule is simply propositions or statements that have facts and rules, and basically they are used for reasoning. They are simply if, then, or if else statements that we use. I think that is a bit clear. On production rules, okay, you read on advantages and disadvantages on the same. I want to move to semantic networks unless somebody has a question on production rules. Thank you, Reinhard. Charlo, we are discussing methods of representing knowledge for AI systems. Is there any question on production rules? I want to go to semantic networks. Okay. You can brush through as we continue. In case you come across something, then you can ask. So it is simply statements that we use to represent knowledge and for reasoning. So in production rules, tunatumia normal English or we use text. We use text. Okay. Now, semantic networks. Semantic networks use graphs. It is a graphical method of representing knowledge. Graphical. So knowledge representation that consists of nodes, objects, and acts that represent the relationship between them. Now, for production rules, si lazima tuchore flowchart, though you can do a flowchart that would represent. It is not a must, but you can use a flowchart to represent. Okay, especially when you're doing programming. So it is not a must, but you can be free to use a flowchart to represent production rules, but it is not a must. Okay, semantic networks, and you'll do flowcharts and other methods of programming when you'll be doing SMA 191. You'll cover that. Now, semantic network is a graph which represents a description. You can have a whole paragraph, and then that paragraph is broken down into a graph. The main purpose is for understanding, just to enhance understanding. Okay. Yeah, so there are three components of a semantic net. It is simply a graph of knowledge, a graph that represents some concepts or some knowledge. It has a node or nodes. Nodes represent objects or attributes or values. A node can be something like teacher or lecturer or student or elephant. Okay, that is a node. What are you describing? Okay, ni kitu gani una describe kwa hiyo knowledge representation? So a node would represent that. A link is a connection between two nodes. It can be just an arrow connecting two nodes. Okay, that's a link. So it can be a relationship between the two nodes. Then a label is a description of the relationship. You describe how node A relates with node B, or you explain the attribute of node A or another attribute of node B. So we represent that using labels. This is a good example. So this is a node where we have reptile is a node, animal is a node, mammal is a node, head is a node, etc. So that's why we are saying nodes represent objects. Nodes represent objects. Okay. Then we have labels. Let's do links first. Link is just the connection. So this arrow, this one is a link. This is a link. This is another link. Okay. This is another link like that. So those are examples of links. Then a label is a description of how two nodes relate. For example, is a should actually be here. That is a label. Is a inafaa ikuwe hapa, alafu is a ingine hapa, instance of ingine inakuwa hapa. So these are labels, that is, they explain how node A relates with node B, or they explain the status of a particular node. Okay, so you can read this as a reptile is an animal, a mammal is an animal, a mammal has a head, so has part head, that means a mammal has a head, an elephant is a mammal, then Clyde is an instance of an elephant. You remember the species and the genus in biology. So Clyde could be either part of that. So it is an instance of an elephant, like that. So this is what we call a semantic network. We have nodes, labels, and the connections, which basically describe something. They describe something. Yeah, so in semantic nets, we use a graph. And this is what we are calling a graph or a chart representing that information or that knowledge. Now, maybe you can have a scenario and then we look at some of the sample nodes. I can mention one or two nodes and then you mention others. We want to do the relationship between Machakos University as one of the universities in Kenya, and then you look at related bodies like Ministry of Education. Okay, we have Commission for University Education, and then we have, for example, student. Yeah, so we have Machakos University, we have MU, so we can have MU, yeah, sorry, let me just insert, let me insert this so that we do it in here. So Machakos University, that's number one. Student, then we have Commission for University Education, Ministry of Education, Education, yeah, okay, lecturers or lecturer, like that. So we can have MU, student, CUE, ministry, lecturer. These can be examples of nodes, these ones. So what I want us to do is to try to come up with relationships, which can be now represented as a graph. Okay, so can somebody give me relationship between student and student? Student here, you can maybe have your name. You can have something like Eric. Okay, so Eric, something like that. So can somebody relate student, Eric as a student, and Machakos University, the relationship between the two, and you give it as a sentence? Sorry, let me give you an example of what I want. Let me relate Commission and Machakos. So you can say the Commission for University Education accredits courses at Machakos University. So the commission, that's what we call accreditation. So that's the same as approval. So approves. The commission approves courses done at MU. So that is a relationship. That's a relationship. Sorry, can I have a volunteer doing student and Machakos University? Yes, Anne? Yes, Anne?
Machakos University approves unit done by the student.
Okay. Yeah, that's okay. Machakos University approves units done by the student. When you register for units, for example, the exam coordinator or the chairman approves on behalf of the university. So MU approves courses done by student. Very well. Somebody else? Bilimo is saying Eric studies at Machakos University. That's correct. The relationship between Eric as a student and Machakos University. Carlo, Eric is a student at Machakos University. Okay. A student at Eric is a student. That's okay. Jeremiah? Oh, sorry, Jeremy. So again, MU, student, commission, ministry, lecturer, those are nodes. Now we are creating relationships between them. How they relate. Okay. How they relate. So I think for student and MU, we've exhausted to make a mean around 3 relationships, which is okay. I already did the commission and the university. So somebody can do Ministry of Education and either commission, student, or Machakos, Ministry of Education. Somebody to try that? Ministry and anything else? Ministry and anything else? Relationship? A trial? Hello? How does the ministry relate? Ministry of Education, how does it relate with these others? Yes, believe me?
Ministry of Education provides funds to Machakos University.
Okay, great. That's good. Yeah, the Ministry of Education provides funds. We normally call it capitation. So provides capitation to Machakos University. That's good. Somebody else can do ministry and anything else. Somebody else can also do lecturer and any other item. Lecturer and any other item. We are trying to relate. We are trying to relate them. Yes, Calvin? Okay, lecturers are paid by the paid or trained? Paid. Okay, lecturers are paid by the Ministry of Education on behalf of government. That's okay. Or Mercy is saying lecturers get funds from ministry. That's okay. That is paid or something. Lecturers are survived or served. Okay, by the ministry. Diana. So there's a direct attachment between the ministry and lecturers. Yes, Levi?
Lecturers are given house allowance by this commission.
Okay. Yeah. Lecturers are given house allowance. That is part of the pay. Osborne, you want to contribute? That's okay, Levi? Osborne, you wanted to contribute?
Lecturer, students.
Again?
Lecturer, teachers or lecturer students.
Correct. That is lecturer and student. So lecturers teach students, or a lecturer teaches a student. And the student of Machakos University, for example. Okay, Anne, you wanted to contribute also? Yeah, so that's okay, Osborne. Yes? Yes.
Lecturers' schedule is arranged by Machakos University.
Okay, the schedule.
Okay, the schedule. Yeah.
Yeah, that's okay. Yeah, that's okay. Yeah, that's okay. Schedules for lecturers are organized by the university. So we do something like a timetable, when to teach, when to be in the office, when to do this, when to go for assessment of students, etc. Yeah, so what we've been doing is just normal English, yeah? Description of Machakos University students, commission, ministry, lecturer, how they relate. Eh? Okay. Joseph, okay, good. I think Joseph is joining. Eh? Yeah, so you can represent this information in a graphical way. So when you come up with this graph that represents what we have just discussed, then it is now called a semantic network. So you can say something like student, you can say Eric is a student of Machakos University. So you start from here. Eric, instead of reptile, is a student, then you say of Machakos University. That is one. You can say John is a lecturer at Machakos University. Okay. You can say, you can add a new node here, and then you say, or you can just use this one. You can say Commission for University Education accredits courses at Machakos University, something like that. So you just do now the drawing. You draw nodes, unaweka hizo, and then you do an arrow and do the explanations the way we have been doing. So it is simply a graphical way of representing knowledge, and we call it semantic networks. I think that's clear. So I want to request us that each one of us at your own time, you can try to create a semantic network from what you have been discussing, how Machakos University relates with student, how commission relates with student or MU, how MOE relates with the lecturer, like that. So you'll try to create something like this. I may not draw it now. Yeah, but we've already discussed the relationship, so you can create on your own. And in our next class, I will sample a few and you will project. I'll show you how you can project from your end so that we see what you have on your phone or on your laptop, and we see it here. I will show you how to do that. So I will sample next time, and then we have it. Yeah, so I will do that. So I will do that next time, but you can try to access. Sorry, you can try to draw, come up with a semantic net using those nodes. Let's move to frames. Let's move to frames. Frame ni rahisi. A frame is also a graph, but now in form of a table. Levi?
Yes, I had a question.
Okay, carry on.
What are the advantages of semantic network?
Okay, in the notes we have a set of advantages down here. I'm trying to avoid that because of time. Yeah,
Yes.
but unaona hapa chini?
Yes.
Hapa kwa slide 49.
Yeah.
Tuko na advantages and disadvantages of each. But anyway, I can just explain. Semantic networks are easy to follow in terms of the hierarchy. They are simple, easy to understand, easy to trace how different things or people relate. It is also flexible. You can easily remove a node from one place and then you transfer to another. Now, the challenge with it is it may be ambiguous at some point. You may not be able to do 100% representation for different components. Yeah, but it is because of the graphical nature, you can easily represent, easily understand, easily make sense of how different objects relate and how they work. I just avoided that a bit, but we have a set of merits and demerits in slide 49, which you can refer to in case of anything I can explain. Is that okay, Levi?
Yeah.
Okay. Thank you. I just wanted to concentrate on the concept itself. Now, for frames, a frame is a tabular representation of knowledge. Tabular, so table. We represent using a table. Tunatumia table to represent. Okay. So the tables are normally divided into what we call slots and facets. Okay. A slot is a sub-element. That is basically part one of the table. It's like column one. You have column one and then column two. Column one, tunaita slot, which is a sub-element of a particular object we are describing. Then facet is an attribute or a feature. So slot is a breakdown. Ukidescribe kitu kama a chair, you can break down the chair into different things. For example, you can say, what is the cost of the chair? What is the quality of the chair? What is the material used in the chair? So cost, quality, material, etc., those are slots. Then now facets are the descriptions. For example, you can say the cost is 50,000. So cost is a slot, 50,000 is the facet. material used. Material, most of it is timber, or you can say timber and some metals, you know. So the second part is the facet. We have an example here. This is an example of a frame, which is an automobile. Oh, it's not very clear. Okay, I think that's now a bit clear. So this is an example of a frame for an automobile. An automobile is like a car, okay? So you have two columns. Column one, this is simply a description. You want to describe a car. Okay? Yeah. So yeah, Charlo, I saw your response. Levy, I saw your response also. Lecturers can be fired by the ministry. Okay, that's okay. Yeah, so for automobile, we have different levels, like class. So class of is an example of we have two components here. Slot is number one. Then transportation is a facet. In other words, what is the category we are talking about and what is the information in that category? What is the category and what is the information in that category? So for example, the class is transportation. The manufacturer is Audi. Origin of manufacture is Germany. The model is turbo. The type of car is sedan. The weight is this, etc. So what are we talking about and what are the details? So that's basically what we are calling the facet and the slot. And it is that simple, just a breakdown. Again, I want us to do a small exercise on that. Let us do a breakdown for a typical computer system. The breakdown. What are the classes? Sorry, the slots and the facets for a computer. For example, I've already done one for a table. So I can start you off. I can do the first two and then you do others. We are doing a frame for a computer. A frame for a computer. That's what we are doing. So a frame for a computer system. I've just reduced that. I wanted to new slide. Okay. Just a minute. I'm trying to insert a table so that I have some two columns. Yes. So you can have something like this. So this is computer frame. Let's start from here. What is the cost of the computer? Let's say 50,000 Kenya shillings, or you can have dollars. The second thing is what is the brand? You can say HP. Sorry, can you continue with the same? Number 3, Bilimo.
Installed RAM, you can say 8 GB.
Sorry? Oh, the RAM.
Yeah, RAM 8 GB.
Correct. RAM capacity 8 GB. That's right. Next.
System type, you can say 64-bit.
Yeah, processor.
Yeah.
Processor type 64. You can say
64-bit.
64-bit processor. Yes, Anne?
You can say the hard disk has a capacity of 250 GB.
HDD 250 GB. Hapo iko sawa. Next. That's okay. Wengine wameenda lunch ama?
No, we are following.
Okay. Levi, tupatie ingine.
Maybe from my side, I don't have.
Okay. Haya, cost, RAM, processor, HDD. Hakuna ingine?
The color of the computer.
There are different colors.
Yeah.
Okay, for example, gray
Black.
or black. Okay. Yeah, color black. Sorry, Bilimo, you want to add something?
Yeah, you can sell Intel Core i7 speed be like 7 hertz.
Or that is still part of processor.
Yeah.
So it can be Intel or i3.
Core
Eh?
i7, Core i7 or 3.
Okay. Intel Core i7 or i3.
CPU
etc.
at
Sorry?
CPU at 2.7 gigahertz.
Okay. That should be CPU speed, eh?
Yeah.
CPU ama processor speed.
CPU speed.
So you can maybe 4 gigahertz. Eh? Yeah, something like that. VHZ. Eh? Very well. So this is an example. Thank you. That's good contribution. Eh? That's very good contribution. Yeah, Levy generation. Okay, sawa. You can also have generation. This should be fifth generation, for example. Eh? What is the generation of computer we're using? You can say maybe it's fifth generation. So these details represent, they can be a frame description of a computer system, frame description of a computer system, just like we have frame description of an automobile there. So the first three methods that we have discussed so far are quite abstract. Eh? They are very general methods. Yeah, Gerald also talked about the model. Eh? Yeah, the model or the brand is the same thing. You can say brand or model HP. So we have what we are talking about. We have the details there. Okay. So this side is what we are calling the slots. And then to the right we have the facets. In other words, what is the breakdown of the object you are talking about? The breakdown of the object, and what are the details on each component of the breakdown? Yeah, so basically that is the idea. So this is the same thing. You can have mammal, elephant, glide, etc. Okay, and yes, Levi?
Can we classify using the size?
Yeah, no problem. Sorry,
Okay.
size for the monitor, for the CPU.
We are speaking about the size of the computer.
Yeah, that's okay. For example?
We have the supercomputer and the, yeah.
Yeah, supercomputer, mini computer, mainframes, that's okay. You can do that.
Yes.
Yeah. So you can
Thank
say,
you.
for example, in terms of size, this is a microcomputer or a personal computer.
Okay.
That's okay. We can use that. Okay, thank you. So I think the details on advantages, disadvantages you'll read. Eh? But so far we have looked at the three, and we are going to the fourth one. Eh? The first one we looked at was production rules. And production rules are simply statements of if and then. If this, then that. If this and this, then that. Eh? So they are just ways of doing communication or reasoning or decision making using else, if then rules. Eh? The second one was semantic network, is just a graph. It's just a graph that you use. Eh? Okay, for representing knowledge. That knowledge can be described as, in a paragraph. You can have a paragraph describing the knowledge, and then you have a semantic network being used to represent that particular paragraph. The third one we have just looked at is the frame. A frame, and frame is simply a graph, a table that represents that information, that breaks down the object depending on what you want to describe as a person. It is you to decide on that. from the details that exist. So I want to shift now to where we ought to have started. I want to shift to propositional logic. Unless somebody has a question on the first three, I want to shift now on this. Yes, I want to shift on this, unless somebody has a question. We are now going to the fourth method of representing knowledge, propositional logic. Did you do part of this last semester? Propositions? Belimo, did you do something on propositions last semester? There are some colleagues of yours I taught some time back, and they are
Yes,
already.
we did.
Uh-huh.
We did
Oh,
under the basic mathematics.
Oh, great. Yeah, that's good. That's good. So it means we'll move very fast on this because it is something that you've already done. Yeah. So a proposition is simply a statement that is either true or false, not both. A statement that is true or false, not both. That is a proposition. Okay. For example, Nairobi is the capital city of Kenya. That is a fact, and it is true. Okay. Number two, Kenya is an African country. Okay. An African country. That's a proposition. Now, propositions can be sentences or mathematical statements. You can have something like 1 + 1 is equals to 0. That is a proposition. 1 + 1 is equals to 0. Okay? Proposition. So any proposition must be true or false. It can't be anywhere in between. If you write something like 1, if you do 1 + 1 is equals to 0, then somebody else does 1 + 1. Now, 1 + 1 is equals to 0 is a proposition because you can evaluate and then you see, is it true or false? But now, 1 + 1 is not a proposition. Why? Because when you say 1 + 1, there is no evaluation, there is no conclusion to it, so that you cannot ascertain what exactly you're talking about. So the way it is 1 + 1, it is hanging. It is not complete. Okay? It is not complete. So it is not a proposition. You say something like Jen is Mark's friend, for example. Jen is Mark's friend. Just that. Jen is Mark's friend. This is not a proposition because we don't know Jen, we don't know Mark, and we don't know whether they are friends unless there is a proof. So it is hanging. You cannot ascertain that John is Mark's friend. You can't. Okay? So a proposition must not be ambiguous. It cannot be ambiguous. And I hope you can confirm what you did last time. Now, two, propositions are represented using symbols. For example, you can have P. So you can have a statement as P, another statement as Q, another statement as R, etc. Three, compound propositions are normally connected using these symbols. The first symbol, this is OR. This one represents OR. So you can say something like P or Q, P or Q. Okay? And, you can have and, P and Q. You can have not Q, not P. You can have implication. P implies Q, P implies Q. You can also have equivalence. Equivalence, you can say P and Q is equivalent to Q and P. P and Q equivalent to P to Q and P. P and Q, Q and P is the same thing. Okay, so we can represent them using these particular statements. Now, when you use OR, any statement using OR is called a disjunction. P or Q is a disjunction. For example, you can say, James or Mark. James or Mark, that is a disjunction. James and Mark is a conjunction. Not James is a negation. James implies Mark. Okay. James and Mark friendship. James and Mark implies friendship. Okay. James implies Mark. That is normally called an implication. So because of the implies. Yeah, so we normally have these details here. Yeah, these are examples that you can have. So you can have P representing a statement. For example, it is raining in Mombasa. You can have Q representing a statement. For example, Eldoret is a city. You can have R as another statement. Another statement. R is not here. Maybe you can create one for the same. So we can have a statement for R. You can say let R be something a bit relevant. It is raining in Mombasa. Eldoret is a city. And just say life is good. Life is good is not a proposition. Nairobi is the capital, of course, of Kenya. So let's say Nairobi is the capital, like that. It will not make a lot of logical sense combining the three, but it's okay. We'll get better statements ahead. So what I want us to do with this page is to read. Hello, are we still together?
Yes.
Okay, thank you, Levi. Somebody else, are we together?
Yes.
Okay, thank you. I won't take too long today. I think 3 or thereabout I should stop. Ikigonga 3, I'll stop anytime. So in the next 30 minutes, sitaenda mpaka 5. Okay, so we can just concentrate to endelea. Now, in this page, I want us to simply read the statements. For example, P. P is, it is raining in Mombasa. So ukiandika P the way it is, iko sawa hivyo. True is just true that way. False is just false. Now, this is P or Q. So in terms of reading, you would have P is, it is raining in Mombasa, or Eldoret is a city. It is raining in Mombasa, or LD is a city. Okay. Not P. Not P is a negation. Not P is a negation. So we would have, sorry, P was, it is raining in Mombasa. So not P would mean it is not raining in Mombasa, a negation of the same. It is not raining in Mombasa. Okay. Yeah, so I think I've already done 1, 2, 3, 4. Somebody can do 5. This is all, right? This is the same thing. It's only that we have added parentheses. So hii pia inamaanisha it is raining in Mombasa or Eldoret is a city because of P and Q. Now, I want to modify this. Can somebody help me read this?
Not.
Yeah. Sorry, I've changed it. This one now. Somebody to read that, yes, Billy?
It is not raining in Mombasa, or Eldoret. Eldoret is not a city.
Okay, that's correct. It is not raining in Mombasa, or Eldoret is not a city. That's right. Okay. You can say it is neither raining in Mombasa nor Eldoret is not a city. Okay. It is not raining in Mombasa or Eldoret is not a city. What about this one? Yes, Kelvin? Are you sure it's the same? Okay, how do you implement this in mathematics? when you do negation of P or Q, I think it should be negation of P and. It should be negation of P and, if you remember. Inafaa ikae hivi, si ndio? When you break down this, inafaa ikuwe negation of P and negation of R. So how do you read it? Bilimo, you wanted to? Okay. Yes, Moki, I'm not audible enough. Levy, the screen. Cyprian, the screen. Osborne, screen. Oh, okay. Sorry, does my screen have a problem?
Yeah, to my side.
Yes.
I have problem. So what I'm following is only listening.
Oh, you're not seeing anything on the screen?
Yeah, I'm listening only.
Yes, Osborne.
Yes, sir.
An example of semantic network.
Oh, so let me share again. Let me share again. Okay, kindly confirm. It should be on propositional logic examples. Is it okay now?
Yeah, okay.
Mutungi Moki, is it okay?
Yes, it is okay, but unasikika uko mbali sana. Speaker yako sijui iko mbali na kidogo.
Okay, so let me move closer to the machine.
Moki aka kwa ufa.
Moki pia songa karibu, mimi pia nitasonga karibu na machine.
Ati niko karibu na?
You can move closer to your machine. I'm also doing the same. Ndio tusikizane vizuri.
Sasa sijui ni earphone ama ni mouthpiece yako ama hiyo microphone yako yenye unatumia.
Sorry. Kelvin, mnanisikia mzuri ama kwa umbali?
Sasa uko sawa?
The sound is good. Maybe Moki anafaa kuweka ufa.
Sasa nimekusikia, uko sawa?
Okay, sawa. Thanks Moki.
Yeah.
Okay. Sawa. Okay. Good. So we were reading this, number 6, So this is it is raining in Mombasa, and Eldoret is not a city. It is not raining in Mombasa, and Eldoret is not a city. When you evaluate this, open the bracket, it will give you this. So you read it as, it is not raining in Mombasa and not or. Eldoret is a city or is not a city. Okay, sawa. So in the same too. We can do this one. Somebody wants to try this? P or Q implies R. Implies to normally read it as then. Sorry, let me just modify this so that ukiwa na hii, we normally read this as if P then Q. If P then Q. I'm reading number 3. If P then Q. Okay, we can also read this as P implies Q. P implies Q, like that. So somebody can apply that to read this. This one. Volunteer. Yes, Anne?
If it is raining in Mombasa or Eldoret is a city, then Nairobi is the capital.
Okay. Okay. So if it is raining in Mombasa or LD is a city, then Nairobi is the capital. Kelvin, you want to confirm? Iko sawa hivyo? Yes. Hiyo pia bado iko sawa? Haina tofauti sana. It's okay. Somebody can also say raining in Mombasa or Eldoret is the city implies Nairobi is the capital. Okay. Yeah, so that is basically how we read, how we read the particular details. Now, the last bit of this is how do we represent propositional logic in a table? We normally represent it using what we call truth tables. Tuna represent tukitumia truth tables. Okay. I hope you also did truth tables in basic maths, did you?
We did.
Great. Very good. So for truth tables, you normally have different columns. You can have column 1 and column 2, that is PQ. You can have 3 columns, PQ and R. You can have 4 columns, PQ, R, and N, something like that. Now, for a conjunction, in terms of evaluation, a conjunction is said to be true if both are true. So these ones must be true for this to be true. That's a conjunction. Disjunction is true if at least one is true. So if there are 2, then inakuwa moja moja. Hapa kuna true moja, na kuna true mbili because of at least. Okay. Now for a negation we simply do the opposite. A true becomes a false becomes a true for a negation. Implication. Now an implication is false if
First.
iko sawa?
Yeah.
If the premise is false and the conclusion is true, is that okay?
If
Or
the
vice versa?
first is false,
The first is false, the second is true.
yeah,
Then it is false. Otherwise, it is
false.
true.
Otherwise, true.
Otherwise, true, correct. Yeah. So these are the basics, isn't it? Zinakwanga the basics that we can apply.
Sir, please re-explain negation.
Oh, negation. Now, a negation is simply the opposite of the initial proposition. Yeah, for example, if we say Nairobi is the capital, the negation for that is Nairobi is not the capital. So if the first one is true, then the second one is the opposite, which is false. So Nairobi is the capital, it is true. Nairobi is not the capital, that is false. Nairobi is the capital, false. Nairobi is not the capital, true. Bilimo?
Okay, on implication,
Yes.
we have an error. It is supposed to be true, false, then that one is false.
So it is false if the first one is, if the premise is false.
Yeah, is true, then false.
That's what I wanted you guys to confirm. Can somebody else confirm that? Somebody else to confirm that? Yeah, that's correct. Bilimo, you are right. You are right. It's an error. So the premise should be true and the conclusion false for it to be false for an implication. So ideally, we should have a TF scenario. Hii ndio inafaa ikuwe false. Alafu hizi zingine zinakuwa true zote. Hii inakuwa true. So the premise must be true, and then the conclusion false for it to be false in that order. Otherwise, it is true. Okay, thank you. I wanted you to confirm that. Yeah, so we normally have different options. Rather, we can use truth tables as one of the ways of evaluating the truth value of a statement. The truth value of a statement. Levi, do you have something?
No.
Okay. All right. So evaluating truth values, we evaluate using this. I just want us to have a bit of an exercise here. Allow me to introduce another screen. Okay, new slide and insert a table. I want us to do some exercise on this. So, for example, we have this. We have P and Q and this. So let this be P, let this be Q, and then we have P and Q. Let me just copy. Sorry, that is P and Q. Okay, we can have not P, not P, not Q. Sawa, tukue na hizo. Now, were you using false and true? Do we apply the aspects of conditional and biconditional? Yes, we can. We can interpret that also, Gerald, no problem. Yeah, so let's try to do this. Mlikuwa mnatumia 0011 hivi ama you are just using the false, the true false? Mlikuwa mnatumia hii?
Tulikuwa tunatumia true and false.
True and false, eh?
Yeah.
Okay. So this is equivalent. So we should have FFTT, and then FT, FT. Okay. So this is a conjunction. Eh? This is a conjunction. What are the truth values for this? And endelea na hii column. Hii ni conjunction. So this is
false.
Then
True. False.
False. Eh?
False. Then false.
False again. Eh?
False again. Yes. Then true.
Then yeah. Bilimo, is that okay?
Yes,
Bilimo?
it is.
Okay.
Yeah, it is okay.
Endelea na negation of P.
TTFF.
Okay, correct. TTFF. Hiyo iko sawa. Osborne, oh sorry, Kelvin. Kelvin, do negation of Q. TF. Okay, hiyo iko sawa. TF. That's okay. Eh? Yeah, so from that, I believe when you're given different propositions, you should be able to evaluate. Eh? Unafahamu wewe able to evaluate. Okay. Now, There's something called tautology. Did you come across that?
Yes.
What is a tautology, Osman?
Tautology is a scenario where they are all T's. The result is all T's.
Okay.
It's all true.
Okay, very well. So that if this is the final column, then you'd have all of them as true, regardless of the other propositions, the proposition of values. Hapo ni sawa? Okay. Contradiction.
Contradiction is all false.
All false.
Yeah.
Okay. Consequent. Consequent. What is a consequent in terms of the results? The clue is hybrid.
Both true and false.
Okay. So you have truth and false at some point.
Yes.
Yeah, the different options. Zingine true, zingine false.
Yes. Lecturer, I'm a mute.
Lecturer, I'm mute.
Yeah, but let me funza.
Oh, sir, consequently. Osborne.
Yes.
Osborne.
Nini.
Can you explain what consequently means?
Okay.
We have
Okay, sorry, I muted. I muted. Now, so consequent is a case where both are true. Sorry, you have true options and false options. Hiyo iko sawa?
Yes.
Now, what is logical equivalence? Logical equivalence. We normally write it that way. Or by conditional. What is logical equivalence?
It's like saying tautology.
Tautology.
Almost the same.
I think the result, the final column for both compared for both compared objects, the final table, the final column is same.
Could be.
For example, if we have not P and Q as one of the one that want to solve, and then the other one is P. If the final result in solving not P and Q, and the final result not P, the truth table is the same, the final column is the same, then they are logically equivalent.
Yeah. That was Osborne, eh?
Yes.
Oh, sawa. Hiyo iko sawa. So the bottom line is the same. So that if you have FFFT for P and Q, Q and P must be the same. So E pia inakuwa FFFT. So the results for this is the same as the results for this. Then we say they are logically equivalent. Logically equivalent. Very well. Who taught you basic maths?
Dr. Ngwava.
Sorry?
Dr. Ngwava.
Ngwava?
Yes.
Okay. Yeah, I did a good job. At least on propositional logic, you guys are good. Eh? Ama mlifanya exam 3 weeks ago. Okay, sawa. So, on propositional logic, I think you are good. Any set of examples that I'll give you, you should be able to. I will post some exercise in the LMS so that you do some practice. But from the assessment for propositional logic, you're okay. Now, give me 10 minutes only. I stop at 5 minutes past 3 so that we just introduce this and stop for only 10 minutes. Any question on the past 4 as we introduce the last one?
Question.
No question. Thank you, Osborne. First order logic. This is also called propositional calculus. Sorry, first order calculus. I'm a predicate calculus. First order logic. Mlifanya hii pia?
No?
Oh, you didn't do this one, eh?
Yeah.
Somebody is saying yes. Bilimo, you did?
We did part of it, and the other part is what we are doing under calculus.
Oh, okay. Okay. Sawa. So it means again on this we are to take long sana, but I just want to introduce it for 10 minutes up to 5 minutes past 3, and then we stop. Now, first order logic. Sorry, there's a challenge. There's a limited in terms of non-expressiveness. It is not so much expressive, or rather expressive enough, because we normally use letters, alphabetical letters, A, B, C, etc., and we don't know what exactly that means. So when you have, for example, if A and B, then C, unless you refer back to the statements, you may not know exactly what A and B and C meant. So it is not expressive enough. That is the problem that first order logic solves. So in first order logic, a statement is normally broken down before we do the hybrid representation. The statement is broken down into objects, properties of objects, relationships between the objects, or the functions that the objects are able to do. So you can have an object. An object is, for example, a person, a house, color, somebody's name, etc. Those are objects. Then you can have property of an object. For example, a person, you can say smart, a smart person. A house, you can say a big house. That is a property. Color, sharp color, for example. So you can have an object and then the property of that object. Now you can create a relationship. Sorry, these are examples of properties: red for color, round, healthy, like that. Now, relationship and function are not very different. That is how two or more objects connect. How are they related? How do they connect? For example, you can say Mark is the brother of Jane. So you have Mark as an object, Jane as another object. Brother of is connecting the two. Bigger than, X is bigger than Y. Okay. M is inside Y. So inside. Okay, part of. Machakos University is part of Kenya. So easy zinapeana the relationship, zina indicate the relationship between objects. And then functions basically are more or less ways of representing relations. Yeah, for example, father of, best friend, this is the best friend of this is the father of this, etc. So the key things that first order logic concentrates on are objects, properties, and how they relate, which can be done in terms of functions. And I want to give an examples in a while. Now, in predicate calculus, we also have connectives. This is implication. In a represent implication implies. This is and, this is or, this is biconditional, which in some cases is equivalent to logical equivalence. So this one biconditional. Sometimes we use it as logical equivalence. Now, quantifiers, we'll discuss that down here. Constants, sometimes we use constants to represent a single object. And for constants, if it is a sentence, the first letter inakuwa capital, for example, M or A. If it is a single letter, that single letter inakuwa capital, kama ni constant. Constant means we only have one representation. We have one thing actually. Variables are represented using lowercase. If it is a letter, we use lowercase. If it is a statement like Mutua, you would have Mutua in lowercase yote. Okay, small letters yote. Alice in small letters yote. Here in a represent variable. Okay. Now, variable represents a set of things. For example, you can say A. A would represent a set of things, not a single thing. X the same, S the same, Mutua in small letters the same. Okay. Predicate is a relationship. For example, before, has color, raining, okay, black, red, and stuff. So a predicate is simply the relationship between two or more objects or the property of an object. Property or properties of an object. Then of course function I've explained. Yeah, so I think we can wind up by looking at some of the examples of how we do the representation just quickly, and then we finish. So we just looked at propositions. Okay, you can have something like round ball. You can say the ball goes without saying, the ball is round. Okay, the ball is round. Jen is smart. Jen is smart. Okay, Jen likes John. Jen likes John. Jen and Ken are friends. Jen and Ken are friends. Okay. If Jen and Ken are friends, then, sorry, if Jen and Ken are friends, then they, I'm looking for a good word here. Okay. Each other. Okay, so what I want us to do with this as we finish is how do we represent this in predicate logic? To represent in propositional logic, you simply have a letter. The ball is round. Ball is round. You just have P. Let that be P. Okay. But in predicate logic, in predicate logic, you'd have a full sentence representation. For example, the ball is round. You identify two things. One, what is the object? The object is the ball. Two, what is the property of the object or how the object relates with another object. So what we're interested in are ball and then round, where ball is the object, round is the property. So the predicate representation of that is, I think I need to do syntax. In your syntax, your predicate logic rep, you normally start with the predicate and then in brackets, object or objects separated using commas. So you do predicate and then in bracket object or objects separated using commas. So in this case, the predicate is round. Predicate is either the relationship or a property. So here we do something like round, and then in bracket, what is the object that is round? We do ball, and then in logic, we normally end sentences using a full stop. So we say round in bracket ball. This is predicate representation of the ball is round. I hope that's okay. Hello? Hello? Yes, members, are we still together?
Yeah.
So Jen is smart, Jen likes John, Ken, and are friends. Let me do number 3. Jen likes John. Now, what are the objects here? Object number 1 is Jen. Object number 2 is John. Then likes is the predicate. Is that right? Likes is the predicate. So from the syntax, unaanza na predicate, we are doing predicate logic representation. So we say like or likes, then in bracket, who likes the other? Jen. So unaanza na Jen. Then you do comma. The person that is liked is John. Then you do a full stop like this. So Jen likes John. So that is predicate representation of that sentence. So unaisoma hivi, Jen likes John. This is the predicate. Sorry, likes is the predicate. Jen is the principal object, the main object. Then John is the other object that is being acted on. Okay. Can somebody try this? Sorry, let me do this first, and then we try the other two and stop now. If Jen and Ken are friends, oh, sorry, it will answer this. I want somebody to try this. Jen is smart. How do we write the predicate representation of that? So you say predicate ni, object ni.
The predicate is smart, and Jen is the object. So smart, then bracket, then Jen in the bracket.
Then?
Pardon?
Full stop.
Full stop.
Okay, thank you. So Jen is the object, smart is the predicate. So we say Jen is smart. So smart Jen. Eh? Very good. Somebody else to try this? Predicate representation. Calvin?
Friends is the predicate.
Okay.
Then in bracket object we have Jane and Jane, comma Kelvin, comma Ken.
All right. So we say friends. Jen first. Eh? Oh, sorry. Jen Ken. This can be either then full stop.
Then full stop.
Okay. Thank you, Calvin. That's okay.
Okay.
So we say Jen and Ken are friends. Eh? So Jen is a friend to Ken. Jen is a friend to Ken, like that, and vice versa. Okay. So Jen and Ken are friends, and so they love each other. So hii iko na 4 parts. Therefore, let me break down because of time, and we have to finish. Tuko na 4 parts. Part ya kwanza. Oh, sorry, in the syntax. Eh? Oh, thank you, Gerald. I should end with a full stop. Eh? Yeah, in the syntax. Okay, thank you. So kuna sentence nne hapa. Jen is Ken's friend. Ken is Jen's friend. They love each other is Jen loves Ken, Ken loves Jen. So how do we express that? Oh, very good, Brian. Oh, in fact, that is good. Now, can you try to type hiyo answer hapo nione vile mnaziandika. Ziko nne. Okay, love, friend, Jen, Ken. Huyu amefanya summary. Brian, umefanya high level summary. Just break down. So iandike hivi. If Jen is Ken's friend and Ken is Jen's friend, it implies that Jen loves Ken and Ken loves Jen. Ziko nne. There are 4 sentences. Sorry. I want you just to arrange them. So friend, Ken, Jen. Hii ndio ya kwanza. Ya pili is friend, Jen, Ken. Hiyo ndio sentensi ya pili. Sentensi ya tatu, is utatumia implies, alafu instead of friend then you say love. You say love, then you again say and. So what I want you is to arrange these four. Okay? If Ken is Jen's friend and Jen is also Ken's friend, it implies that Ken loves Jen and Jen loves Ken. Put that in one sentence using the implies. Just try to type it there. Na hiyo ndio kitu ya mwisho tunafanya, alafu tutaendelea na predicate next week. Who is trying? Bilimo is typing. Somebody else can also type. Okay, sorry, I've seen some responses. Okay, love friends love Jen, Ken. Okay, Bilimo. Yeah, Ken is Jen's friend and Jen is Ken's friend. It implies Jen loves Ken and Ken loves Jen. Okay. Yeah, friends love. Charlie, you've done a summary. Yeah, the answer that is close, very close to the correct one is Bilimos. The one that is very close near Bilimo, that if Ken is Jen's friend and Jen is Ken's friend, then, so we'll reiterate the symbols vile tunaweka. Then Jen loves Ken and Ken loves Jen, full stop. So hiyo ya Bilimo, this one, hiyo ya Bilimo is the most correct. Okay, hizo zingine pia, they are close. They are close. Yeah, so I think because of time, we'll not proceed further. So we will pick from there for predicate logic. We'll pick from there. I want to open the floor for any questions. You can type or just talk. Any questions from what you have discussed today? Any concerns? We agree that we'll be meeting now officially on Monday at 1, like we have met today. Yeah, so please, I open the floor. Any questions now? You can type or just comment. We have improved today. We were around 25. Last week we were 20. So 5 more people today. There are some 15 people who are still lost. I don't know. Mercy, tutafanya aje ndio we bring everyone on board? Mercy Wanjiku, kuna wengine bado hawajamanage kulogin. What are we doing so that we bring them on board? And this is the time also to ask a question. Gerald was asking how physical and introspection as types of AI are implemented. Okay. You can implement physical, both using robots, because you'd mimic the human being. There are some robots that have been developed which are very intelligent, and they actually learn with time. They learn themselves and they improve with time. So you can use robotics. Gerald, you can generally use robotics to do that kind of an implementation. And robotics is part of mathematics, computer science, and electrical engineering, because of mathematical modeling and that. Okay. Yeah, welcome, Gerald. Sorry, we want to finish. I was waiting for any question or anything. Yeah, Mercy, their friends can call them. I don't know whether they normally access the group WhatsApp for the class. If they're able to